Hi, and welcome back to astronomy. We're going to continue our discussion looking at analyzing light. Light is how we observe everything in astronomy, as we discussed last time. So we're going to take it a step further, and we're going to understand how astronomers actually use light to determine what kind of objects they're looking at. So just a quick rundown of what we're about to get into. We're going to talk very briefly about what light is, understanding light as both a wave and a particle. We're also going to talk about how we use light for analysis. We have a couple big items here, such as Wien's law, Kirchhoff's laws, and the Doppler effect. And each of these is going to give us a little bit more information based off the light that we're observing from various objects. And then we're going to talk very briefly again, because you're going to do a research project on this. We're going to talk very briefly about how we collect light. Just a couple of the different types of methods, if you will, the different types of instruments, but it is the basic idea for any part of the EM spectrum. So let's get started. So when we're looking at light, light is something that takes time to travel. You can see an example of this when we're looking at Jupiter. If Earth is close to Jupiter, in terms of our orbit is close to Jupiter in its orbit, then what we're getting to see as the moons of Jupiter orbit around the planet, what we're getting to see is that the moons will actually eclipse, they'll fall behind Jupiter's shadow a little too early. What that means for us is that we're seeing these moons go behind Jupiter sooner than expected. Okay, so if our orbit is further away, we're at a point where we are at the furthest point of our orbit from Jupiter. What we get to see in this instance is that the moons are actually eclipsing a little too late, so later than expected. And so what we're seeing here is that a difference in the distance requires more travel for light. So light is taking the extra time that it needs to travel the extra distance. We estimate this traveling speed of light as a constant c, which is around 300,000 kilometers per second. So if we look at light from stars, or any glowing objects, honestly, light from a glowing object will emit an entire spectrum. And what this means for us is that we get to see basically all the colors. Now, the EM spectrum, the electromagnetic spectrum, which we haven't dived into just yet, is more than just colors. But for now, think of the entire spectrum as a range of colors. So if we look at the sun, obviously don't look at the sun, but if we look at the sun, we collect light from the sun, we're going to see a range of colors when we split it with a prism. However, we can also feel the effects of the sunlight. So we can feel the heat, if you will, the radiation. We can also see in some cellular changes that DNA can be damaged because of sunlight. That's where you start to get things like skin cancer, for example. So what we're getting to see is if we put a prism between us and an object that is emitting light, the light from that object will be split or refracted so that we're able to see the individual waves, or wavelengths rather, for each one of these individual pieces of light from one object. Now, the ability to split light is actually critical for our ability to analyze light. So let's talk about what light is very, very briefly. Light is considered to be an electromagnetic field disturbance. So what that means for us is that we have an electric field and a magnetic field, and these two fields are proportionally attracted to each other. And as these fields are attracted, what will happen is they will propagate through space, meaning they will move through space. And they will have a very specific wavelength and frequency based off of the energy that has been, if you will, put into that wave or into that field disturbance. So the electric and magnetic fields move at 90 degrees. So if this is electric and this is magnetic, then what will happen is as this field shrinks, this one comes in, so on and so forth. It's very hard to coordinate two hands at once, so bear with me. But you get the idea. So you're seeing a three-dimensional propagation of two different types of waves, two different types of fields, an electric field and a magnetic field. But what this does for us is it actually gives us the basis for understanding the electromagnetic field or the electromagnetic radiation that we will get to observe over many different wavelengths based off of the energy input. So this is our electromagnetic spectrum. The electromagnetic spectrum is actually showing us all the way over here on the left where we see wavelengths that are very, very short, and those are gamma rays. Those are very high energy, and because they're such high energy, the waves behave a little bit more like a particle. As we go all the way to the right, you start to see radio waves, and you have examples of radio waves very clear in your everyday. Radio waves will give us very long, very low energy, indicating that we also have low frequency within our wave. Visible light is actually right in the middle, give or take. So if you go from gamma ray all the way to radio, it goes gamma, X-ray, ultraviolet. After ultraviolet is where we get visible. Now the visible range is what you and I can see. These are all the colors of our spectrum. Notice how small our visible spectrum is compared to the entire electromagnetic spectrum. So going from visible, we go into infrared. And this is where we start to feel a little bit more of that radiation from the sun. We also feel it in ultraviolet. Then you start to get microwaves. Microwaves are a little bit longer, they're a little less energy. Microwaves, if you have a microwave oven at home, same kind of radiation that it's using. And then you go into the radio waves, which are the lowest wavelengths. So if we get into frequency and wavelength, we start looking at that relationship. What does it do for us? Well, frequency, when we're talking about it in terms of electromagnetic radiation, frequency is simply the number of occurrences that a wave will use to pass a fixed distance in a given amount of time. What does that mean? Here's point A, here's point B. If I have a wave that is going in one motion here between point A to point B, that can be measured using a terminology called hertz. So that's going to be our unit. So 1 hertz is going to be 1 wave per second. So going back to my example, if this wave took 1 full second to go from point A to point B, then that means that is 1 hertz. Now let's say, still fixed, point A, point B, let's say a wave in 1 second can travel 100 times in here. Well, that would then be 100 hertz. Let's say it's 1,000,000. Well, that would be 1 megahertz. So this is where we start getting into very large numerical values for waves because of the frequency. So if you look at something like your cell phone transmits using light at 2.4 gigahertz. So it's actually sending out a lot of waves at very high frequency so that it can transmit. Now, wavelength, let's talk about that. If I'm looking at wavelength, it is pretty much what you would think. It is the length of a wave. It is a physical measure of length. And we're looking from crest to crest. So here's a wave. I'm looking crest to crest. What I can do in this relationship is I can set my frequency equal to a proportion where I have my speed of light, because that's a known value, it's a constant value, divided by the wavelength. because I know the distance between A and B to measure my frequency. Excuse me. Because I know the distance between A and B that I can measure my frequency, I can measure the length of the wave that is necessary to move over this distance, so that if the wave is this big, I can calculate how many waves will actually occur within that distance, which is, again, the frequency. So that is allowing us to have a relationship between frequency and wavelength. What we see is that a higher frequency requires a shorter wavelength. Okay, so let's take a quick example, just a quick calculation check. If I'm looking at the wavelength of a radio station that is broadcasting on FM 90.L, what is the wavelength? Okay, well, that's an easy calculation. We know the frequency is 90.0 megahertz, correct? Fantastic. So what we're going to do is we're going to calculate using that relationship of frequency is equal to speed of light divided by wavelength. And we're going to flip it around. We're going to say that the wavelength is equal to the speed of light divided frequency. Just do some algebra there and you can see how those terms are moving. Once you throw in your values of speed of light, which is constant, and your 90 megahertz or 90 million hertz, you can actually calculate your wavelength to be about 3.3 meters. What that means is if you look from the base of the door, any door, to the door handle, at an average height, that's about 1 meter. So the wavelength in this case is 3.3 times that value. To put that into another perspective, this is only about 2 meters away from you. So what that means is we're actually seeing a very long wavelength, and that makes sense because we're transmitting over radio waves. They're lower energy, but because of the lower energy, they have much longer wavelengths. So as we see light travel, going back to what I was saying earlier, if light is traveling with a very high frequency, a very high frequency means that the wave is actually acting more like a particle because it is moving so that the wavelengths are extremely short. Okay, that also means we have higher energy. So a higher frequency, you get a higher energy and you get a shorter wavelength so that the light acts more like a particle. Go to the converse of that. Let's go all the way to radio waves. If we're looking at radio waves, they are very low frequency, which means you get very long wavelengths. As a result, you also have lower energy. And because of the long wavelength, you also have more of a wave-like structure. So if you've ever driven by power lines and you're listening to your favorite radio station, and then all of a sudden your radio's cutting in and out because it's getting static, well, what's happening is the power lines are actually at the right length to disrupt your electromagnetic radiation that's coming to your transmitter. So it's disrupting your radio signal and then giving you a poor quality sound. So here's the big question. How can we use light to actually analyze things in astronomy? So how do we use light in general? So the first thing is this. If you think about the sun, we can feel the radiation of the sun. We can feel its sunlight. You go outside on a sunny day. If you're standing in the shade, it's kind of cool. You walk outside into the sun and it's like, oh my gosh, it's so hot, or it feels warmer at least. So anyways, we're out here looking at how we can use that particular inference, that particular observation rather, to infer the temperature of the sun. Well, we're observing the light. And according to Wien's law, the higher the temperature from an emitting object, such as the sun, the more intense the light and the shorter the wavelength. That makes sense, given what we know about frequency and wavelength. But Wien did something else. Wine actually gave us the ability to calculate the temperature based off of the maximum wavelength from an emitting object. Now, it's not necessarily something that you have to do in terms of this class by memorizing the equation, but understanding the relationship that the maximum wavelength, or what we call the peak wavelength, is in a direct relationship with temperature. That's amazing, because that's telling us that we can find the relative temperature of an emitting object by simply looking at the wavelengths of that object. So what we're seeing in this diagram over to the right side is you see your visible light spectrum very clearly pointed out to you. And then you see your wavelengths going from 0, very, very short, all the way up past 3,000 nanometers. And the visible wavelength spectrum is just very, very small within that entire range. What we're seeing are those 3 black curves. And notice that each one of those black curves actually has a temperature. So if you look at the smallest black curve, the one at the very bottom here, notice that it is about 3,000 Kelvin. Its peak wavelength is just around 1,000 nanometers, just under that actually. If we look at the next smallest curve here, it's measured at 6,000 Kelvin. Its peak wavelength is in that blue-green region. And then if we look at the highest possible temperature here, we're seeing 12,000 Kelvin. That largest curve is peaking just before the visible light spectrum. So it would be peaking somewhere in more of like an ultraviolet range. Now, if we're looking at this overall data, this overall spectrum, given the 3 different temperatures, what we're seeing is that the hotter the object, the more energy it would have. Okay, that means we should see its peak wavelength at a shorter range. So we're seeing that peak wavelength of the 12,000 Kelvin coming far before the lowest temperature, which is 3,000 Kelvin, which is peaking around maybe around 1,000 nanometers, and the 12,000 Kelvin, is peaking maybe around 200 to 300 nanometers. And so when I'm looking at this overall spectrum, that is giving me the idea of temperature related to wavelength. So just as a quick reminder, in case you're not entirely familiar with the Kelvin system, Kelvin is used to basically work like a temperature system like Fahrenheit. To make that conversion, you can use F is equal to 1.8 times the quantity of K minus 273 plus 32. K being the Kelvin, F being the Fahrenheit. Just as a general guideline, you can think of a couple base temperatures and items that you can use to reference the overall Kelvin system when reading astronomy text. We say that around 80 degrees Fahrenheit is about 300 Kelvin. So you can think of that as possibly the surface of the Earth, something very close to that range. Something like the surface of the Sun is measured at about 5,800 Kelvin. Again, we use that wavelength temperature relationship to get that estimate. And we say that's close to 10,000 degrees Fahrenheit. Okay, so which wavelength of the light would our Sun emit most if its temperature were twice its current temperature of 5,800 Kelvin? If we use Wien's law, we can say that temperature is going to be equal to this 0.0029 Kelvin conversion divided by the peak wavelength. So that's that lambda nanometers. So what we're going to see here is if we throw in our peak temperature, we rearrange this problem so that we get wavelength is equal to a relationship with temperature. If we put our Sun's temperature of 5,800 Kelvin into this problem and we double it because the problem is saying twice its current temperature, what we find is that our peak wavelength for our Sun is 250 nanometers. Well, if you think back for just a moment to that graph we just saw, The graph actually showed us a 6,000 Kelvin star and a 12,000 Kelvin star. And if you notice, the 6,000 Kelvin star, something close to our sun, peaks inside of the visible wavelength. But the 12,000 Kelvin star peaked more in the ultraviolet wavelength, something that is outside of our normal eyesight range. So if our sun were twice its current temperature according to our calculation, what we would see is that our sun's peak wavelength would actually be in the ultraviolet region, not in the visible region. Why that's actually important is because if you think about it, from an evolutionary stance, if you will, is we are able to observe things in the visible light. But that's because our sun is peaking in the visible light. That's the spectrum that we actually see. If you were to look from Bob the Alien's point of view, who grew up around a star that peaks in the ultraviolet, what Bob would actually see would probably be different than what we could see, because his vision would be more in the ultraviolet. It would shift downwards. If you were looking at Sue the Alien over by a red dwarf star, which is much cooler than our own, Sue's vision would probably be more in that infrared peak range, that spectrum, not necessarily invisible. While visible might be partially visible to them, it would not be entirely because of the difference in energy levels. So this is actually a pretty cool relationship between temperature and wavelength. Now, here's the other really cool thing about light. Because we're looking in our visible spectrum, we might see an image when we're looking into the cosmos. We might see an image much like the image on the left here. Very cloudy, couple pinpricks of light here and there, but overall very hard to discern any kind of information from any one object because the visible light is just everywhere. So we have to filter based off of what we know in our overall concept of light. We have to filter out different wavelengths. And sometimes that means we have to use instruments that are going to be very specific to a wave range. So if we use an infrared camera, instead of an optical device that is collecting light for the visible spectrum, if we use an infrared telescope or an infrared camera, we would actually be able to see through the gas and dust of this cloud. And so you would see an image a little bit more of that to the right side. This is actually the same object in the sky, but notice the visible light on the left and the infrared on the right show two totally different types of images. So together, we can get a better understanding of what is the composition of that cloud, as well as the objects in it, and even some of the objects behind it. So that is enabling us, using the overall light spectrum, to find out some information about objects that would otherwise stay hidden if we could only see in one part of the entire spectrum. Now, here's what's really cool. In class, I like to explain this with the idea of kittens, because everybody can relate to a kitten. Not everybody can relate to an atomic structure. Just sorry. So, if we're looking at the Bohr's atomic structure, so we're looking at the Bohr's atom, electrons orbit around a central nucleus. Now, if electrons are being excited, what will happen is they will jump to a higher energy state. Much like a kitten. So if a kitten is at rest right now, and you go over and you start playing with the kitten, it automatically has some kind of energy input, and then the kitten is responding by being in a higher energy state. But what happens when that kitten gets tired? They fall back down into a lower energy state, which means they go to sleep. Well, electrons inside of an atomic structure leap and fall pretty much the same way. You add energy, they leap, they go to the next energy state. But they cannot sustain that energy state if energy is not constantly put into the atomic structure. So they fall, just like the kitten did, and then they emit light that was the energy input. So they actually are re-emitting light, allowing us to find a very specific type of chemical element by identifying that wavelength. Now, we haven't gotten there just yet, but we're going to. This is actually showing us the ability to analyze light to determine chemical structure. So, if I'm looking at how I can determine chemical structure from light, let's take a very simple experiment. You can see the diagram on the side. If we have a light source and we know what the light source is, then what we can say is if we add some kind of chemical to that light source, in this case we're adding a salt to a flame. As we filter this light and we split it, so we refract light through a prism, we will see the light of the actual light source as well as the light that is being emitted due to changes, that salt that was added. What we're seeing are very specific wavelengths that are in this case being emitted. And so from that emission, we're actually going to use Kirchhoff's laws, which define spectroscopy, an entire science of analyzing light for chemical composition. We're going to use Kirchhoff's laws to determine what is this chemical. Now, that's an awesome thing. It truly is. But Kirchhoff's laws actually give us a little bit more than just chemical composition. They also give us the ability to measure very specifically where certain elements are emitting or absorbing light within the spectrum. If we're looking at objects a little bit later, we're able to measure differences of what we should expect to what we observe, and then what we observe again later to determine if that object is also moving. So let's jump into Kirchhoff's laws. Kirchhoff's first law says that if we have a hot opaque body or a hot dense gas, it will produce a continuous spectrum. And you can think of this as a complete rainbow of colors without any spectral lines. That would mean we have a perfect spectrum. This is also considered to be a black body. An ideal black body has no absorption and no individual spectrum lines that you would see due to basically discrepancies, things like gases, etc., that are added. So a perfect black body, an ideal black body, will have a perfect spectrum, full emission. Okay. Kirchhoff's second law. If we introduce to that hot black body a transparent gas that is hot, an emission spectrum will actually be created. An emission spectrum is simply a very concise series of bright spectral lines that are observed on a dark background. So in this case, you're able to see right down here, we're able to see that we're seeing very specific spectral lines that occur at very specific wavelengths. Now, that is identifying what is actually in the gas. So that hot transparent gas between the light source and you, the observer, after light has been split, after light has been refracted, that is identifying the chemical in between. Kirchhoff's third law says that if we have a cool transparent gas in front of a source of continuous spectrum, so in front of a black body, then we should see absorption lines. But get this, whether the gas is hot and then creating an emission spectrum, or cool and creating an absorption spectrum, the wavelengths of the atomic structure that's being observed in the gas, the wavelengths will occur at the same exact wavelength, the same exact location in the spectrum. So that means whether the gas is being hot because it's being excited, it's already got energy that's coming in and it's essentially emitting its own light, or whether the gas is cool receives energy and those electrons fall back down to a lower energy state, what we're seeing is that the chemicals are emitting or absorbing light at the same location in the spectrum. That's a consistent piece of evidence right there that allows us to actually analyze that gas cloud. It's amazing. Now, if we think about Kirchhoff's laws, as I was saying before, shifts in the wavelengths according to Kirchhoff's laws of what we should expect to what we observe will actually show us motion. So if we combine Kirchhoff's laws, really building up all the concepts that we've talked about so far, and we add in motion, we get something that we call the Doppler effect. Now, you're all familiar with the Doppler effect. Just turn on the weather. They're going to show you these giant rain clouds that are coming through, and you're going to see how they're moving. What they're actually doing is they're using Doppler radar to measure by sending a light signal out to the cloud. It reflects back to the station. They measure it, and then they measure it again, and they see how much it's changed from one measurement to the next. And so using that measurement system, they create the animation that you get to see on the actual radar. Well, in astronomy, or spectroscopy in general, this is what we call the Doppler effect. So the Doppler effect says that if an object is moving towards you, it is being blue shifted, so it is gaining energy coming in your direction. Okay, so if the object is moving away, it is actually red shifted. It is losing energy from your perspective. Here's an easy way to think about it. If you were to watch a car from a very far distance, you hear a low rumble. And then as the car is coming closer, and then as the car passes, right? So you're actually hearing the rumble increase. It's gaining energy. It's getting louder as it comes closer to you. It is blue shifted. As it moves away, it is losing energy from your perspective because you weren't moving, but the object is now moving. So as that object is moving away, it is red shifted. And so it is losing energy from your perspective. That's the Doppler shift really in a nutshell. But we can really go further with the Doppler shift. We can get very precise with our measurements. And this is where Kirchhoff's laws of understanding where those chemical elements actually occur within the spectrum is very important. Because if we say that we're looking for an observed wavelength over what we expect for the wavelength, then we should have a relationship of velocity with the speed of light. Velocity in this case being velocity of the object, or the speed of the object. So if I'm observing a star in astronomy, and I say, with looking at this last question down here, how fast and in what direction is a star moving if it has a line that shifts from 486.2 nanometers to 486.3 nanometers? Well, let's try working this out. We're going to use the Doppler shift rules here. So, given this information, we're going to calculate velocity out of our relationship with Doppler shift. That gives us a ratio so that we have velocity is equal to the speed of light times the observed wavelength over the expected wavelength. So the change of the wavelength is what we're really interested in here. We're looking at 486.2 nanometers and 486.3 nanometers as our two measurements. What we're going to calculate is simply by putting into our measurement system 486.3 minus 486.2, that is giving us the change of wavelength, that is the change that is observed, divided by what we should expect, the 486.2. That's going to be the critical component here. Now, the speed of light, I abbreviated it. You're probably wondering, where does this 3 times 10 to the 5th come from? That is actually just an abbreviated version of the speed of light. It was included right here for you. Pop this into a calculator, you find out that your velocity is actually 61.7 kilometers per second. That is a very fast speed. Now, keep in mind, we're also asking in what direction. Is it blue shifted? Is it red shifted? We're actually seeing that this object is red shifted. It is moving away, and the way you can tell is that you're moving from 486.2 to 486.3 nanometers. That is an increase of wavelength. Because the wavelength got longer, we would see it lower energy, and so that would mean that this object is red shifted. It is moving away. Okay, so now that we've talked about how we analyze light and what light is, the big question then becomes, how do we collect it? So in astronomy, probably the most common instrument and probably the most useful, especially here on Earth, is a telescope. So if we're looking at what is a telescope very simply has many different types of designs, but it is a way of collecting light. So if we use a telescope in, say, an optical sense, we're trying to collect light in a visible wavelength or even an infrared wavelength. They're very, very similar. We're going to use something called a primary lens. And the primary lens is simply collecting the light, and then it's going to focus the light or concentrate the light into a single point for us. We call that a focal point. And we're going to use two key items here to collect our light. That primary lens, in terms of its size, is what we call the light collecting area. And then the ability of the telescope to actually resolve objects is what we call angular resolution. So if we're looking at our light collecting area, the light collecting area is quite literally the size of the primary lens. And this is going to determine how much light you can actually collect. So if you have a 4-inch lens, you can collect 4 inches worth of diameter of light. If you have a 10-inch lens, that's 10 inches, then you're going to be able to collect a diameter of 10 inches worth of light. Now, what does that actually mean for us? Well, if we look at how big telescopes are, the largest telescopes that we currently have on Earth are approximately 10 meters across. It's 10 meters diameter-wise. Remember, 1 meter is from the base of a door to about the door handle for an average sized door. So 10 meters is pretty big, just saying. In space, they're not that big yet. So in space, what we're seeing is that some of the largest telescopes that we actually have are maybe about 2 meters. 2 meters, not 10. So what is the difference in our light collecting area? Well, what we find out is that we calculate the area of a circle for that 10-meter telescope and for that 2-meter telescope. And we find out the difference here is about a 25 times difference. That means the 10-meter telescope collects about 25 times more light than the 2-meter telescope. Now, what does this mean? In astronomy, bigger is better. The bigger your primary lens, the more light you can collect, the better your image. So, let's talk about our angular resolution. Angular resolution is simply going to give us the minimum angular separation that a telescope can actually distinguish. What does that mean? That means if I'm looking at a binary star, for example, and it looks a little bit of a blob, just a single blob, my telescope does not have an angular resolution that is strong enough, if you will, to see two separate stars that are very close to each other. Instead, it sees blob. That's all. Now, what we're seeing is that the angular resolution for a telescope will also determine how far away we can really truly see. So this is really what we call the ultimate limit for a telescope. It is the ultimate limit of resolution when we're looking at the interference of light. Now, Let's say you're looking at an object that is outside of your angular resolution. You're going to start getting diffraction rings, like what you're seeing in this image. You can see the object in the center, but because this telescope is not able to actually resolve the image nicely, this object is far too far away, we're starting to see diffraction rings, those little concentric circles going around the entire image. That distortion really makes this image not usable for us. So, what's good? A telescope that has a smaller angular resolution allows us to look at smaller separations between objects. So that's going to be the best possible solution. Now, here's the big debate in a lot of science. But if you're trying to invest money into an experiment, in astronomy, what we like to do is try to invest money into either a ground-based experiment or a space-based experiment. Ground-based experiments, they're pretty expensive. Space-based experiments, not trying to put a pun in there, but they are astronomically expensive. So what that means for us is we have to determine what is the best method to conduct an experiment. And that comes back to how are we going to try to analyze light, meaning what light are we trying to collect, so that we know what to build. On Earth, we can only see a handful of wavelengths, if you will. We can see the visible, we can see infrared to a certain extent, and we can see radio, because radio is very long wavelengths. Our atmosphere will actually block out a lot of the other wavelengths. Now, in some cases, we can put telescopes on, say, aircraft, low Earth orbit instrumentation, such as a LEO rocket, or maybe even a weather balloon. It really truly depends. But a lot of these objects, in terms of their stability within the atmosphere, may not produce the best results. So, to get the best results, we have to actually get out of the atmosphere as much as possible. That means for us, we have to put telescopes into orbit. So space-based telescopes actually give us the ability to really see the entire electromagnetic spectrum, which is not observable from the surface of Earth. However, keep in mind, again, it is very, very expensive, and that is why we don't do it for every single telescope that is ever projected in some kind of proposal. So we have to have a really strong backing as to why we're building a new telescope. So, if we're looking at optical telescopes, these are telescopes that you're probably more familiar with. Maybe you had one as a kid growing up, or maybe you have one now as an adult. But optical telescopes are very limited in terms of what we can actually see. They are designed so that we really analyze the visible spectrum. And if you have a backyard telescope, you're not even analyzing the spectrum, you're just really looking at the objects because of how small the diameter is, generally speaking, on a backyard telescope. So there are two major types of designs here. There's also some blended designs that are out there as well. But the two basic designs that I want to talk about are refracting and reflecting. A refracting telescope is one that has a glass lens on the front, and then the light will actually pass through the telescope's primary lens, and it will bend, so it is refracting, hence refracting telescope. A reflecting telescope actually uses mirrors, hence it reflects the light. Now, when we're looking at a telescope, it's very important to know that the eyepieces are magnifying the focal point, so the point where that primary lens has bent the light to. But the telescope is not magnifying the object. The telescope is simply collecting the light from the object. That's all it is. The eyepiece will magnify the light that is focused. Okay, so if we're looking at this particular diagram of a refracting telescope, you can see that you have your primary lens right here, This is also called the objective lens, and this is typically made of glass. If you see the light coming in from this direction, this is starlight, that will hit the lens. It will then bend, but when it bends, what will happen is it will actually get a distortion. So notice you have a distortion where you see 3 separate focal points over on the right side image. What you're seeing in these 3 focal points is that the wavelengths for blue, green, and red, as well as the other colors, which would be at other focal points, are not concurrent, meaning they do not occur at the same place. And that is because a prism by nature is refracting light, and then it's creating chromatic aberration. It is splitting the light so that it focuses at multiple wavelengths, multiple points, if you will. Now, for observational purposes, if you've ever had a backyard telescope, if you've gone outside and you've had to toggle the eyepiece back and forth to get a clear image, even though you know you're focused on the object, if it's a refracting telescope, I guarantee you still have a little bit of a fuzzy image. That fuzziness comes from right here where you have that chromatic aberration. You're not able to get a perfectly clear picture because what you're seeing is that the light is actually split. Now, that being said, if we build really, really big refracting telescopes, there is a limitation because a refracting telescope uses that glass lens in the front. Glass is very heavy as a material. And so if we have a very large telescope lens, we have to design A, something that's actually going to support it, B, a place to house it, which is generally part of the support system, and C, you have to consider that once you start getting this very large lens, you might actually have gravitational sag, so the weight of the lens pulling down as it's actually settling. So as the lens is created, it will sag down. What that means is it will distort your image. So how do we get bigger telescopes? If we use a reflecting telescope design, we can actually get a very large, very durable telescope, and it's often much cheaper to make than something like a refracting telescope. But you have to consider this. The light from a star that is coming in, or from an observed object, comes into the telescope, it bounces off the mirror, and then it actually focuses in front of the mirror. Now, you may be saying, okay, why is that important? Well, I'll tell you a quick story. Isaac Newton, who this telescope is actually designed after, because he was the creator of the Newtonian telescope design, Isaac Newton actually created the first reflecting telescope that was then used with a secondary mirror. The first version that he had, though, had no secondary mirror. He would look at an object that was behind him, the light would focus, and he would use his eye as observation. But if you're holding a telescope here, looking at an object behind you, you're in the way, which means you're blocking most of your image. So Newton actually created the design so that it used a secondary mirror, like the one you see here, that will divert light away from the overall focal point that would naturally occur, creating a focal point that's still inside the telescope and then magnifying it so that it would actually divert to your eye. Now, you may be saying, okay, you're still blocking some of the light. Yes, you are. The secondary mirror, by comparison, if you have a large collecting mirror like this, the secondary mirror may be this big, which means you're actually blocking a very small portion of light, and that light loss is acceptable because you're not actually splitting your light and getting chromatic aberration. Reflecting telescopes do not have that issue. Reflecting telescopes actually reflect light perfectly as it is observed. So a reflecting telescope design, again, is more durable, it is less expensive, and it has no chromatic aberration. That is probably the biggest selling point for astronomers. Now, you may have heard of something called adaptive optics. And then let me just quickly explain. Adaptive optics is a computer simulation. So we're collecting data over a series of images, but because of our atmosphere, if we're trying to take very long exposures, what will happen is the atmosphere moves, and it moves very rapidly and randomly. That being said, we take a series of smaller, shorter images, and we're compiling this data together and then analyzing where all of our hotspots are occurring. The hotspots in this case would be stars. And then the adaptive optics, as a computer program, will compile data so that instead of having an image like this one, we will actually get an image like this one. So instead of a blob, we may actually be able to see our binary system. Adaptive optics is very expensive, and it is something that is on professional telescopes, very large professional telescopes. It is not something that you will find on a backyard astronomer's telescope unless they have somehow invested a ton of money into the telescope. We also have radio telescopes. Radio telescopes are a very interesting design. This is something that, again, we can use here on Earth. And to be honest, it's not entirely feasible to put a radio telescope into space. It's possible, yes, but it's not feasible. Here's why. If you look at the two images that you're seeing, in this first image, you probably recognize this from the movie GoldenEye, 007 GoldenEye. This is actually a very large telescope. So large that if you look at all these trees that are around it, these are very big trees. They are full grown. It sits in the middle of a forest almost. And so this large telescope that you're seeing is collecting waves that are sometimes kilometers in distance. That is very long wavelengths. Remember, our radio station wavelength is 3.3 meters. Something in the visible wavelength would be a fraction of the size between my fingers. So what we're seeing is this is a very long wavelength. It is something that we would not necessarily be able to put into space because of its size. If you look at this image down here, this is actually a radio telescope array. And these are all individual telescopes that you're seeing, but together they work together. We call that radio interferometry. And the radio interferometry uses multiple telescopes that are spaced out. They all focus a little bit separately angular-wise, but they all focus on the same object, and they basically collect light over a much larger distance. Now, because of the size of the waves, this region that I'm highlighting would not be collected, but that's okay, because the waves are so long that these objects in between, these telescope dishes, if you will, would be able to collect enough light to discern what the actual object is. Now, professional astronomers do not just rely on any one telescopic device. No, instead they may make an observation, they discover something, they see a phenomena, and they want to observe with other telescopes. And so they'll send out an alert worldwide to say focus your telescopes, if you can, on this object, on this location. And then if you can see something in other wavelengths, that's allowing you to collect more data over multiple wavelengths to explain that phenomenon. So just a few space telescopes, because I don't want to give too many spoilers since this is what you're also going to be researching. If we're looking at some of the space telescopes, remember, we cannot see all the wavelengths from here on Earth, especially high energy. We have to send our telescopes out into low Earth or even a higher Earth orbit. We probably all recognize this middle image. If you haven't guessed already, this is the Hubble Space Telescope. The Hubble Space Telescope does allow us to see in the visible wavelength. Now, it has some instrumentation on it, so that we're able to collect a lot of different images. And it has gyroscopes so that we can navigate back and forth. We can get to a very precise location in space that we're trying to observe. Most space telescopes have very similar designs in that same respect because they need them for navigation. You've probably heard of Chandra, and you probably have heard of Compton. And what you're seeing are these are different telescopes that are observing over different wavelengths. So you're looking at Chandra, you're looking at the X-ray. So the Chandra X-ray Observatory. And then this is the Compton Gamma Ray Observatory. So it allows us to see the entire EM spectrum using a multitude of instrumentation, both Earth-based as well as space-based. So you survived Unit 2, understanding how we actually analyze light in astronomy, as well as collect light. So that being said, please make sure you review all the supplemental materials. Excuse me, I can talk. Make sure you're going over those supplemental materials, and then if you have any questions, email me. If you're also, if you haven't done so already, make sure you're participating in the week's discussion board, as well as the assignment. And again, it may take me 24 hours to get back to you via email, but again, try to email me if you have any questions. All right, guys, have a great week.